Hi there. Welcome. This is a presentation over chapters 24 and 25 for Earth Science 1. And what we're going to do here is a presentation that will allow us to focus on the things that are most important for us to be able to view whenever whenever we're looking at different types of things throughout the chapter, particularly things we may not have talked about because we've had some delays and some challenges this winter. So this is the first thing I'd like you to pay attention to. Take a second. You can pause the program and read through this and then try to figure out what's going on. Notice the date at the bottom. Although this presentation will be isolated about 15-20 minutes, you can easily go back in time, and you're familiar with how to negotiate a YouTube as far as fast forwarding, reversing, and pausing. So take a second and read this. This affects all of us. And one of the things that's happening, which is odd, is similar to what we talked about in class with articles like this. We seem to get one every year. This is one that's posted and from 2012. So do look at that and see if you can find out why that is something that we do have an effect from whenever we see these types of things. What's happening? There's a change going on with the resources, and that's an important link in this chapter. When we move on from that, then what we see is a traditional resource, which is crude oil, and we're having to move farther and farther off land to be able to see those traditional resources. So when you see these types of these types of content, and when we get into these types of formations, particularly like right in here, a lot of these types of wells are having to be deeper and deeper water wells. And what I mean by that is we used to be able to get oil off of land. Well, we can't do that anymore. And the reason why we're unable to do that anymore is because we are having some different changes within our energy resources, and that's pretty tough. So whenever we see those types of contents change, and we see those types of wells and they get deeper and deeper water, that doesn't mean we have plenty of a resource. That means we're actually having less and less of that resource. This is a typical offshore rig, and this is a pretty large platform. So this would be a platform that when you arrive to work, you did not get to come home at night. So think a schedule similar to a firefighter. You're going to go arrive at work. You may have a shift of maybe 3 days, 4 days, or an extended 5-day period, and you are very, very self-reliant. So because you're so far off the coast, you can see some islands in the background or some geography in the background, some coastline there. You have to be able to fight your own fires. You have to be able to do certain things that a 911 call would certainly be in effect whenever we were on land. Whenever that we get off of shore, ever so often we have accidents, and you've probably had some memory of this Deepwater Horizon oil rig that took place. That was a disaster in 2010. BP was the company. You can see that up here. And what we have in this part of the screen is this odd looking light brown material. This is all crude oil. So we were in the water and we were getting farther from the coastline. So we used to be able to get things like crude oil from our coastline. We're having to move farther into the water, and this is the Gulf of Mexico. And when we put a brig right there at the red dot, and that rig is actually this. If we have a problem with that rig and something happens at the upper sections and we don't cap that lower well off, then we have crude oil directly affecting the ocean above. And that's a problem because oil is less dense than water, and we get to see this affect areas like this. So here's what we're seeing in some vacation spots, and you've noticed this in some of your areas that you go to, particularly if you go to the Gulf states. In certain areas, we are now seeing these rigs, these oil wells that are offshore in our horizon, and that's not very appealing. And the reason we're starting to see those in vacation areas is because we're becoming limited on the areas that we can put those in. When a catastrophe happens, it's significant. Remember the flammability issues and the explosive nature of some of these gases associated with petroleum products. So when we have a fire out in the offshore rigs, one of the things that is very problematic is how to shut that down. So the first thing that has to happen in a sense of a catastrophe, like in 2010, we have to help and maintain, preserve life of the people that are working on the platform. Then we have to contain the damage of the platform itself. Next, we have to get down to the bottom. Remember, there's a tether. Remember those first diagrams we saw? There's a tether that goes down to the bottom of the ocean floor, even if it's a moderately shallow ocean floor. We're having to get into deeper and deeper water. So once we do contain this and we have chemical spillage at this level, then we have to try to get underneath this platform and cap that spill off. And that's a problem. One of the things that are commonly done whenever we have these types of situations is they intentionally burn the oil off of the surface of the water, and that helps control it, because when that oil goes to the coastline, it certainly affects wildlife and it definitely affects tourism. None of us would like to go to a vacation spot and not be able to access the beach because of large globules of crude oil washing up. So unfortunately, that was the case in 2010, 2011, 2012. One of the things interesting about this slide is if you look at the laser pointer area here, check out that little bitty tornado-like structure. That's because of intense temperature differences, and that shows you how hot this fire is. It's a very unusually warm fire because of the intensity of the petroleum adding fuel to that fire, and it eventually melted and caused a lot of problems to the metal members of that structure. This was a backup structure. So believe it or not, we have mobile structures like this that are backup structures that can be put over these wells that have those tethers that are leaking and causing a major amount of oil to come out of the bottom. And so what can occur is a boat similar to this can pull one of these structures out, and ideally they're going to hook to that structure. That's a lot easier said than done. It's a very, very difficult situation. You've got moving oceans, you've got extremely high pressures of gases and extremely high pressures of crude oil being emitted from the bottom of the ocean, and it becomes a problem that is just not being very productive as far as stopping that issue. So here was the problem. There was a hole in the bottom of the ocean floor. This is the Gulf of Mexico again, that BP put in, and you can see that that's a horizon drill. It drilled down to about 18,000 feet below the surface, and that is underneath 5,000 feet of water. So we had, during this event, one of these structures fail. We had a massive fire. That structure failed, and this umbilical, these lines between that and this well, broke. That umbilical was left on the ocean floor. We had massive amounts of crude oil being pushed out of this intentional fissure, this well, and it was being billowed up to the surface of the ocean and polluting in unprecedented masses the Gulf of Mexico, one of the worst in human history. And the problem was that we created it. So the idea was that this temporary structure was going to create a new umbilical, drill down, create a relief well, intercept this original well, and relieve some of that pressure, and then this was going to be capped off. That didn't work. That was a very, very, very challenging situation in a lot of original attempts. So eventually they did get it, but it was a very hard situation. And a lot of people around the planet were learning about the hazards of offshore drilling. This was the apparatus that you see here. So that gives you an idea, this little red piece, that gives you an idea of how large this apparatus was. If I were to stand next to this, my top of my head would be about right there. So these are large processes. That gives you an idea of what type of energies are involved there. The reason this is shown is because this should have been a cutoff valve. This is where the umbilical goes up to the platform, and this apparatus right here should have automatically shut off when they had a disconnection. Unfortunately, because the breakage occurred, they had a partial breakage occur right here. They couldn't operate as engineered. This is crude oil. This is what would float to the shore whenever you were at vacation or your favorite vacation spot in the Gulf. Major problem to clean up. It collects together. It is very dense in some areas, but it still has the ability to float to the surface, but it's not directly on the surface. So quite an ecological and environmental disruption. You can see how the spin of the Earth is causing that. We've got a little Coriolis effect going on there. And then we get this light, almost like chocolate milk material here going toward the beach. That's all crude oil that you see here floating toward that beach. So a big problem when we see that. Definitely people that had livings maintained from boats like this. You probably recognize that as the shrimp boat. They were employed because they didn't have any work. You can't eat shrimp out of water or fish out of water that is polluted with this level of crude oil. But they were hired by BP to skim the water to try to maintain that. This was a very, very difficult process. And that's what we see when we try to get too aggressive with offshore drilling. And that's unfortunately what we're having to do to maintain our appetite in this nation for crude oil. Moving on, here's a few things we should know. You're doing very well with this. Hopefully these points are reinforced on your quiz. You have renewable and non-renewable resources that you're doing well with. Remember your lab you did with the Indiana MAP project. Make sure you can know where these pockets are. We have gas wells and oil wells overlapping within these areas, and these are pipelines. So Indiana is a state that does have gas pipelines within it, and we do have some oil refinement within those. Hopefully you can remember what this was. This is what the discussion connected to where your drinking water was from. This is your Ohio River. Here's where we have a well that grabs that water, not directly from the river, but it goes down and it grabs water that's embedded within rock. The rock acts like a filter, and this would be a residential well. So remember that we get our water from the ground. All of our drinking water comes from the ground, whether that be surface or subsurface. Most of it is subsurface. One of the things we need to talk about yet in class, which we will do before our exam, depending on when you're listening to this, is lighting facts. One of the things that's crept up in your lifetime is a lighting fact sheet like you see here. Doesn't that look like something on the side of a candy bar or something that you would eat? And it kind of gives the calories. That's what we're doing with lighting. Because in this nation, we have a significant challenge of how we're going to use less energy, because we are going to eventually start closing power plants that are coal-based, and we have to have some alternatives, or we have to use less. And so this is an attempt by our nation to help consumers choose light bulbs, because we have a lot of light bulbs in our house that will last longer. Notice 1.5 years for this one, and this one is 5.5 years, and not only last longer, but they're going to use less wattage. So you have 13 watts for the one that lasts longer, and you have 60 watts. So if I were comparing two light bulbs and they both produce about the same amount of light, then one of the things I could look at to make a wise choice to help reduce our national need for electricity is choose the light bulb that is on the right. This is what it would look like. You can see that, and a lot of you are probably using lights similar to this. These are called compact fluorescent lights, or CFLs, and they have a kind of a pigtail view of light bulb there. A lot of times they're occluded in some type of a bulb shape here that makes them look a little bit more like our incandescent light bulbs that we're used to having, the ones that produces a lot of heat. Incandescent light bulbs are light bulbs that whenever they're working, you've got to let them cool down before you touch them. Most of that energy goes into heat, which is why we want to get away from using those. We don't want to heat food with light bulbs, or we don't want to heat the inside of our house with light bulbs. We just want light, and that's why this is a good step to take. Many of you may have had households within your families that have received compact fluorescent lights for free by your energy producer. And so say an entity like an REMC, like Harrison County REMC or Duke, those are energy producers or energy suppliers that might give their customers compact fluorescent lights, because that helps reduce the strain of energy on the grid. Here's what we see being pushed across the nation. We're trying to get people to understand across the nation to buy lumens instead of watts. So if we go back here, notice how you have watts. That's at the bottom of this list. Lumens is what's really important. That's what allows us to see. So when you walk into a bright room, there's a lot of lumens in that room. So if I want a light that is going to be not only efficient, but also producing a lot of light that helps me see, what I need to buy is something that is lumens. And if you notice on this package, it's published very clearly. So when you're trying to choose lights, don't go after watts, go after lumens. Lumens are what allows you to see. Then we can calibrate that based on the type of technology it is, and so on and so forth for the app. There's a lot of hues of light. We have soft white light, we have incandescent light, we have a very institutional white light, so on and so forth. Fossil fuels are something we spend some time on. There is a discussion board that we should have participated in in My Big Campus that relates to these. The one that we need to look carefully at in your book is tar sands and oil shales. These are alternative methods of getting crude oil from, and we are typically not using those unless if we're running out of crude oil in more traditional areas. So in the past, we used to be able to get crude oil over land. We're nearly out of that in this nation. So we have to go to water. That's hazardous, and it's also environmentally damaging when problems happen, like we saw in 2010 with the Horizon hazards. So we move to land again, and we can get oil from sands. It's called tar sands. Sounds like Tarzan. Tar sands are one of the things we can use, and we can use oil shales. These are shales like the ones that you worked with in your geology lab. They do have oil in them. It is hard to get that out, and it's expensive. This is kind of our third or fourth or fifth or sixth choice to use because it makes price per gallon expensive. And we typically buy gas by gallon in a range that has to be around $3 for most of our consumers to be comfortable in this nation, is what most research seems to be leaning toward. So take a second and read through this in your book. You've got a nice graphic, a good chart and map that shows where those are. This is our traditional oil well. A couple things here I want you to pay close attention to. We have to have cap rock above and below this. I'm going to refer to this as a seam. This is a seam where water occupies, like you saw in the Gulf of Mexico with the Horizon explosion, with that well rupture. Oil will always go on top of water because it's less dense. Gas will go on top of oil because it's less dense. So the order of a well's interception with these products is after it goes through cap rock. This is a pretty dense rock that doesn't allow gas, oil, or water to move into it easily. So it might be something like granite or a very dense sandstone that's moving into a quartz type, a tighter quartz configuration. So what we would intercept if I were drilling a oil well on land is very dense rock, not anything like limestone. Then I get into a pocket of gas. Unfortunately, what we did in the past with a lot of this gas is they just allowed it to go off to the atmosphere. That's why a lot of times they would know, oil drillers would know they were close to oil because the gas would stink, and they would smell those hydrocarbons, and it would stink like a lot of times rotten eggs, which is where our liquid propane mercaptan gas comes from. So a lot of times you can smell when you're close to being out of liquid propane because of a indicator odor that's intentionally put in those gas tanks called mercaptan. It is replicating the smell of rotten eggs on purpose. That's because when we smell rotten eggs associated with natural gas, we know we have an explosive environment. So what oil drillers used to do is when they smelled the mercaptan smell, which is really natural gas, they would ignite that and allow a controlled burn off of all that gas. They just wasted it, in other words. Then they got into what they were after, which was crude oil. Because when we first started using crude oil, human history could not use the gas above it like we do today. Today, we're going after a lot of this gas because what we're learning is that this gas gets into this rock around it, and we're fracturing that rock to get that residual gas out. So that's kind of the interception, and that's pretty important to understand because that relates to the science of the density, gas over water, and oil over water. So the order of that arrangement, gas, oil, water, with two cap rocks. Formation of mineral deposits. This goes into something that goes back to chapter 24. Do make sure you can understand the simple definition of ore. This is something that's useful to us. We have a couple ways that this can form. We have direct contact, our hydrothermal type of associations here. And then we have something that's regional. So even if it's in the region and it gets warm, we can have some ores that's deposited. Placer deposits are something that occur in water that's running. Placer deposits are what gold miners in the gold rush, whenever we were trying to have a westward migration, were after. And that's where you saw those gold miners using water and panning for gold. Placer deposits simply are a process of density where we have something like gold or silver that gets carried by water. When the water velocity slows down, the more dense material, gold, silver, will settle to the bottom, and we can pan for it. So three things here that we need to connect to with this: placer deposits with water, contact metamorphism, and then we have these hydrothermal processes, and this blue or purple area is supposed to be water. And then we have the regional. So three things can make ores for us. We have the hydrothermal vein deposits. We have contact metamorphism, which is directly contacting this igneous pluton. And remember, a pluton is igneous material moving into that goes with igneous rock. And then we can have regional. It doesn't have to be connected with a hydrothermal vein. It doesn't have to connect lava or magma, but what it can connect with is just hot rock. And all three of those will produce the ores. Moving forward, we have non-metallic mineral resources. These are things that can be used for their physical and chemical properties. So these are processes that are typically referred to things like minerals that you studied earlier in the course, the ones that we tested over. You can see fluorite in the list. So look over this list here and make sure you can connect to two things that are resources in the surface of the earth, non-metallic like this, and then we have some metallic resources that we see that would be connected to something like this. Let's move forward and get into alternative energy sources. This is more along the lines of Chapter 25. Chapter 25 opens up talking about traditional energy resources that are biomass related, similar to coal, but they are non-renewable. So what you need to make sure you can do is speak about or show a proficiency of the formation of coal, the formation of gas, and how crude oil forms. Those are all pretty critical in this type of a study. Alternative energy sources are where we need to move because these are sustainable. There's a 25 of 25 national initiative, and our goal is pretty ambitious in this nation. This has been tweaked just a little bit, but hopefully by year 2025, which happens to be the year that we want to have our first manned missions to Mars by NASA, we're going to have 25% of our domestic energy. So potentially, when we have the first human, first American on Mars from NASA, we would be using 25% of our energy from a alternative energy source. So what are these alternative energies? You know some of them. We talked about solar energy. There are two types of solar energy that are used. We have passive and active. Passive systems are systems like big windows that don't have typically technology or moving parts within that. Active systems are systems where we have to buy technology or use certain machines that allows the circulation of something like hot water, or it changes the position, or it transfers energy to batteries. We have two advantages of solar energy, and these are pretty intuitive. You can probably think of them. What are they? They are that solar energy is free and solar energy doesn't pollute the atmosphere. Solar energy can be used in shingles. The state of Arizona is using this technology. Why don't we use this in Indiana? You can probably think of a few pretty good reasons, but a very innovative way to use the space on your roof, which is ample, that can collect energy from the sun. And notice how thin these panels are. So areas of the world where we have large hailstones, areas of the world where we have freeze-thaw cycles, or these get covered up a lot with snow, those are problematic. But areas of the world or areas of our nation where we don't have those concerns, we can certainly use them. And they actually have an aesthetic value. Notice how the grids are divided here, and it makes them look like the regular asphalt shingles that are common throughout our nation. Nuclear energy is within the alternative energy sources. This is not necessarily an alternative energy in the sense of renewable energy. This is not renewable. We still have to have uranium. So an important learning goal here is to understand that we need uranium-235. It's bombarded with neutrons. That's considered a trigger. And what we do is heat water. And then it becomes that process that we talked about in class that generates steam. And then the steam turns something called a turbine. And then that's where we get the energy that drives that electrical field that we send electrons down power lines for. So the uranium is split. This is fission. Don't get fission mixed up with what we talked about in astronomy. The thing that goes, the process going on in the sun is fusion. So fission is where we split nuclei. What are we splitting? Uranium-235. Uranium-235 is in small quantities in the Earth's surface. So we have to dig out a lot of uranium from the Earth's surface and change it to a different type. Uranium-238 is a little bit more prevalent in the Earth's surface. And then we can change that and refine it to 235. Areas where we refine it typically have to be maintained with a lot of policy because of the potential radiation pollution from uranium. One of the worst places close to you that has been a national disaster because of radioactive misconduct. We didn't know exactly what we were doing when we were developing radioactive materials in earlier human histories was in Paducah, Kentucky. That is a Superfund site, and we are still trying to clean that up. That's pretty close to you folks. Here's typically what happens in a nuclear process. You have Diablo Canyon. This is a nuclear power plant. Notice you don't have any emissions from this. That's considerably different than this outline. Although it's poorly drawn, this is the outline of cooling towers that are in Ohio and in Illinois and Michigan. Sometimes the cooling towers do have steam coming from those. That's not radioactive. All that is steam. Water is associated with nuclear power because it's a moderator. We can use water to help cool the uranium in the fission process. We can also use lead and some other products. So one of the nice things about nuclear power is it has no emissions. It just needs this water to go into a reactor that's going to keep things cool. Problem is, if we have a reduction of the water, or if for some reason the pumps moving the water to that nuclear reactor, then we have a meltdown because the nuclear reactor gets too hot. Then we have a fire like we did in recent past whenever we had the Japan earthquake that was extensive, and they had a meltdown of a core, produced a fire, and then the smoke was radioactive. So we still have some concerns with this process. Where do we see these types of nuclear power plants? Well, they're about everywhere except in, wow, Indiana, Kentucky, West Virginia. Look at this pocket. Why don't we have too many in this area? Cheap coal. This is coal country, folks. So around that area, we are surrounded. We've got like an island, a no nuclear island right there. We are surrounded, flanked entirely by nuclear power. So we have in Indiana and Kentucky and Virginia had pretty significant success in keeping nuclear power out of these states. Downside is, in the Ohio Valley right here, we've got some pretty significant challenges with our air quality. We've got a lot of coal power plants in Indiana. Same thing in Kentucky, West Virginia. So over the time, you're probably going to see those cleaned up. In the next immediate futures, in your early professional life, you will probably be seeing a lot about nuclear plants being closed. Moving on, wind energy, you know these. 50 to 60 years, we want about 10% of this country's demand for electricity from wind. And you've seen these if you've traveled north to Chicago or north in Indiana. We're using a lot of wind turbines. These were the earlier generations. They are very pollution free. However, they're noisy. And these types of things are the processes that we're learning about. They also are pretty high maintenance. This is a larger one. This is a pretty neat design, a lot of innovation. This is a proposal for a steerable. Notice how it's on a turret. This can be steered into the wind. That's not these. These guys can't be steered. They're all facing, they're all looking the same direction. However, if we can have a design where we could turn the turbine, the props, into the wind, we could harness that even better. And we could harness wind even better. So if the wind is from the northwest and then it shifts to the southwest, we could turn this appropriately. Notice how it has a steerable vane. Pretty innovative design. That's something that's coming out of the Department of Energy lab in Argonne, Illinois. Look how big these are. These are mammoth turbines. We're pretty serious about developing power from wind in this nation. So here you have a couple individuals doing maintenance on this. Alstom has created a mammoth turbine here. So you get an idea of where the wind fields are in Colorado and how large these processes are. This is the level that we're going to have to get to, folks, if we want to get 10% of our energy within the next little bit from wind power. So remember our goal, 50 to 60 years within your lifetime, to get about 10% of the country's demand of energy. We got to get away from that coal is what we're moving to. Here's the inside of that. What's nice about these, this is a 2010 opening, and this is in the United States. So these are not foreign jobs. These are good jobs. Many of you might even be employed by these types of industries as we move forward into this new initiative in the country. We're testing these all around the world. Look at Indiana. Remember that coal pocket? Well, we've kind of offset that. We've got about we've got a good range. We've got about 1,500 to 2,000 turbines, mostly up in this area, but we are looking at developing that. This is a fairly windy part of the nation. right in here. Not so much for us in southern Indiana, but hopefully this will be a first and important step to get us away from coal power. Offshore wind generators are pretty neat. These are able to be moved in the ocean so we can grab that wind that is always present over our ocean waters. So pretty unique process here, still in development stages. Big problems here is when we have disruptions of the ocean water. These can be expensive and problematic to get to whenever we need to hurry up and move those out of the way of a tsunami, or if we got a hurricane, so on and so forth. Those natural events that occur can make this problematic to move. Also, harnessing the energy and bringing it to land can be quite expensive. We need cables connecting that to the mainland. Hydroelectric power, you know about these. These are things that we do see when water begins to fall. We have some of the largest dams on this in this nation that are like Hoover Dam or the Grand Coulee Dam. We do have a hydroelectric power plant in part over the Ohio River. If you've ever been to the Falls of the Ohio, you've seen that. They've got some warning signs up because they do control the release of that water. Pretty simple process. You've been hopefully aware of this for quite some time. We do need a reservoir, and then the water falls, and what we get is a massive reservoir behind an embankment that's typically a gravity-based embankment that's thicker at the bottom and thinner at the top, and it's made of concrete. And then we're going to control the release of that water. Basically, we want to pile water up as high as we can and then let it fall. When it falls, we're going to control what it falls through, and they have turbines in there, and those turbines then spin. Geothermal energy is what we use when we're harnessing the steam from within the earth. So a few slides ago, we looked at hydrothermal processes that made ores. We look at those geothermal processes as energy as well. Basically, we're after hot water and steam. So instead of letting something get water hot, the earth is already making hot water and steam like geysers in certain parts of the nation already. So why not use that to generate a motion in a turbine? So areas of the world where we have steam like this, like geysers, we can channel that energy together and we can get that moving and cause turbines to move. Geothermal power plants are different than heat pumps. So there's two things that we'll talk about in class that you need to make sure you have a good understanding of. When we say geothermal power plants, what we're talking about is power plants that are using steam-based energy like this. However, some of your households might have a geothermal heat pump that is not using steam in the ground. Indiana households have geothermal heat pump. Some of you in the class have a ground source heat pump. It makes energy more efficient in the household. In other words, the house can heat and cool for less expense. We're using heat in the ground. You've been in a cave before and you've noticed that the temperature in the cave is always about the same, around 55, 56 degrees. People have noticed that for some time. In the late 70s and early 80s, they designed a system that circulated the fluid into the ground to keep the temperature moderate. So then the house could be partially maintained in temperature with that moderate temperature. Here's how a geothermal heat pump for individual use works. This is not steam-based. Okay? There's a little confusion because of the wording here, so make sure you understand that. Geothermal power plants are steam. Geothermal heat pumps are using the heat that's stored in the ground. This basically uses a loop system, and one of the largest that we can see is a Galt House East. This used to be the biggest one on the planet. It's in Louisville. And the reason why is because instead of using loops like this, they're actually drilling down and using wells instead of water. They're using well water that's well in the ground, using the temperature that's moderated, and they're using that fluid to moderate the temperature inside the building. Very efficient process. So this is where the Galt House is, and that process, this building right there, is being heated and cooled partly by water that permeates through the ground from the Ohio River, and that maintains a certain temperature. Then the building can circulate that temperature inside the building by a fluid, typically a refrigerant, or by direct contact with the water, and then they move that heat around. So it allows the building to work less as far as electrical needs to heat and cool. We're not building too many of those anymore because it does disrupt our water source. We need the water in the ground to drink, not necessarily to keep a building hot or cool. That's the Galt House. You've been there before, potentially with some functions or maybe even stay the night. All right. Current residential tax credits are available through 2016. They're probably going to extend these. So some of your households moving forward, maybe they'll extend this through your lifetime, because we are having a strain of energy on throughout the nation. You can get a 30% tax rebate. We'll talk about that in class a little more. So here's a practice problem. If we have something that we buy, say we buy a system and it is a geothermal heat pump and it's $1,000, you get a 30% tax break from that. So really, you're going to get $300 back for purchasing that. So in effect, that $1,000 purchase was actually costing you only $700, which is a pretty powerful leverage whenever you want to use that year after year after year, because you're going to be spending less. Moving forward, let's talk about tidal power. This is not widely embraced across the planet. We're going to use the motions of tides, in and out, high tide, low tide, high tide, low tide. And they can use a small dam over an estuary. This is where fresh water meets salt water on the planet. So that inflow and outflow can be used. So low tide, here's your little small dam, and then the high tide moves through, water gets trapped, we let it fall. So it happens. High tide, then it comes back out to low tide, and then high tide, and then low tide. It always is moving things around. Pretty neat concept. Downside is you can't get your jet skis past here. So whenever we're out at some of these famous beaches that we like to vacation in Florida, we're not going to put these up there because it's going to reduce our tourism. So this has to be in areas that are fairly remote. Well, if they're fairly remote, we don't need a lot of energy, but it can be used. So there has been some sample projects, but overall, not a widely embraced system. Moving forward, we have to make sure that we understand that this is a water-based planet, and we have some freshwater pollution sources. We talked about this in class. We did a discussion board over it, but do make sure you can understand these 2 points. We have a non-point solution that gets into our water that is from multiple sources. Point solution is from one particular source. This might be from a factory. This might be from a specific fire, or it could be from a catastrophic train wreck. We know the chemicals that were being carried by those train cars got into your water whenever we had a massive pileup during that one wreck. That's a point source. Non-point source is, man, there's a lot of material that gets into our water from a little bit of this property and this resource or that, so on and so forth. And so that's where we're getting non-point. So everybody contributes to that. An example of this is typically agriculture related. So when we find pesticides, stuff that we put on plants so that bugs don't eat our plants, because they like the food that we grow too, we have to put something on there to keep the bugs off. Well, if we do that over hundreds of thousands or millions of acres across the country, and then it rains, those pesticides flow off and they get into your water. But we can't say that it's just from one farm. It can be from multiple, thousands, or millions of farms across the nation. That's non-point source. However, a point source is one particular event, typically at one particular time, or over a certain percentage of time. Runoff is what carries that forward. Here's some types of what major water pollution. Make sure you're familiar with the types of examples, the sources that relate to those examples, and the type of those. So, for example, disease organisms. We can get sick by bacteria and viruses. Those are examples. What are the sources of those? Improper waste treatment. We don't have our waste treated before we put them in, or we have floods, or we have failed septic systems like we talked about there. What do we get from drinking those? Typhoid, dysentery, these types of processes that are problematic. Cholera. Those are things we don't want in our society anymore. So take a second and read through those. Make sure you're familiar with a few examples. We do have pollution in the atmosphere, and this is what the last discussion board of this chapter range of content was focusing on. We've got some pretty significant challenges in the Ohio Valley, and we do track particulate matter. That's 2.5 micrometers, which is extremely small, and we want to watch that. Not only do we have our global warming that is gaining momentum and almost hard to deny in this year, in 2015, but we also have pollution that we're breathing in as well. So take a second, read through these. Make sure you're familiar with primary pollutants, nitrogen oxides, carbon monoxides. We know where those are from. Those are transportation. Stationary fuel sources, sometimes that's a little confusing. That's something like a power plant or something like an industrial process, a factory. Industrial processes would be more specific like a factory. So do look at those two pie charts and make sure you can make sense of that. Land resources, we definitely have some resources there. We have damage, typically erosion when we get into that. So when you did your Indiana map project, you saw that we had a lot of surface mines for coal, and we stripped that coal off, and that created a major problem. And you're probably aware in certain areas of Kentucky, particularly eastern Kentucky, they're reducing mountains. They're causing mountains to no longer be peaked at the top. They're cutting the tops of those off because there's coal in there. So there's a major damage to the land resources when we get into those. Mines cause soil erosion and pollution. The pollution can be wide ranging. Mainly what we can see there is acidification of surface streams because it releases acids that should be contained within the ground, but when we excavate, then we allow those acids to flow more freely, and that can cause death to streams. How does a stream die? The stream flows, but nothing can live in it, so it's sterilized. So you don't get any fish, and everything around it's dead. And what we notice in Green River in Kentucky and in some other case studies is that we're having massive, massive ecological shifts. There are certain species that simply can't live in those waters anymore, or will have massive deaths during the summer months or certain times of year of certain fish species. Here's an example of a surface mine. So it's difficult to see. It's not the best image here, but this is a large surface mine, and this is being excavated. So think bulldozers, think high lifts, those types of things that are scooping out the Earth's surface. This is normal. And what we're doing is instead of having this go up like it did and back down, we're carving down and we're getting the resource out. We do that with things like copper, aluminum. That's how we get that out. Gold. Sometimes we go after silver into those. We go into very deep sections that are open pit mines and are extremely, extremely disruptive to the Earth's surface. We need to keep the water clean and safe, and we've recognized that in this country. So we have methods of conservation, which are careful use of the resources there. We also have a Clean Water Act. In the 1970s, we realized that we had a couple disasters and we were mismanaging water. We just weren't caring about it. Some people on the planet said this is not good policy. We have to have water to survive, and we can't maintain a healthy way of life for water's polluted. So therefore, what was born in 1972, the Clean Water Act. And this caused a reduction or eliminating point source. Remember that point source pollution. We were using water in industry to dump waste into. This is why so many of you know that the Ohio River is not a high quality stream. We still use this water source to dump waste into. Why? It carries it away. And so we put that into those, we put those waste into that. And the industrial processes are typically much more significant, much more poignant than that of our household. So major challenges there. We're improving that, but this has been a very effective act that we continue to use in this nation to help keep our waterways and our groundwater safe and clean. The Safe Drinking Water Act of 1974 was established. This is why your household, by federal law, receives a report of what you're drinking. You have to be told. Whether or not you pay attention to that is up to you, but you are in writing, you have to receive this. You get a little pamphlet, and what they tell you is where your water system was compromised, what it is you were drinking, what happened, and what was done to eliminate the problem. So that's a very important policy. Clean Water Act, Safe Drinking Water Act that you need to be aware of. Here's how we can prevent water pollutions. Browse through these. These are things we should all be doing. Unfortunately, we don't think about water as a resource. We expect it to be there all the time, and it probably will be. Whether or not we can drink it and have the quality of water that we expect today is going to be somewhat questionable if we do not do these. So we don't want to put toxic chemicals in the ground. Don't dump the oil on the ground after you change it. Put it in a receptacle. Make sure you take it someplace where they can handle that waste. Don't put things that contain hazardous substances, batteries, old computers. Don't put those in the trash. They've got mercury in them. Mercury will contaminate our water. We will have an extremely difficult time getting that out of our water, and we've already failed with removing mercury or keeping mercury out of our food system. So those are things that we should learn about and do a little better job of. How can we protect the air? Well, in the 70s, we also had a Clean Air Act, pretty busy year. So we had the Clean Water Act and Clean Air Act. This is one of the most wide-ranging, successful clean air acts that helps our nation have clean air. What we started in this area, in this era, was something where we could track based on standards certain criterion pollutants. Those are led by these: carbon monoxide, those are from vehicles; ozone, lead, sulfur dioxide, nitrogen, and particulates. These are what we track in the Ohio Valley. Why do we track those? They're not good for us to breathe. Why do we have those? Power plants and vehicles. What type of power plants? Coal. Why do we track those? Why do we care about them? Because in the 70s, we said that we were not going to have a healthy population of nations of people if if we were breathing air that was polluted. So we said, what do we need to track? These things. How are we going to track them? By this, the NAAQS. That is a system we still use today. How can we save energy, which is in effect improving our air in the Ohio Valley? Because the way that you get energy at your house is by a plant somewhere that you don't see burning coal. Well, try to recycle. Try to let sun heat things up. Try to do these types of things. And so much of this depends on your lifestyle, but those are things that you can help reduce that. That'll do it for the chapter. That gives us 2 chapters. Remember, this is 2 chapters of content that we see. So whenever we're looking at the different types of contents for your next exam, remember that you have 2 types or 2 chapters that you need to be aware of. You have chapter 24 and chapter 25. So thanks for tuning in. I'll see you in class.